School 2024, let's have a Google Doc and write down a bunch of topics of things that we think people might be interested in, and then we'll get people in Vesri to vote on what they would like at the summer school. And, to encourage the team, I thought, I'll put a bunch of stuff in there, I'll throw in some really left field suggestions that no one will vote for, and, why don't I give a talk about this thing? And I kind of put this title down. And then a bunch of you voted for it. And I was like, okay, right, you really want this? So this is your own fault, okay? You voted for it, so I'm doing it. Okay, so what can abstract mathematics tell us about programming climate models? So we're going to be talking about a branch of mathematics today called category theory. It's a kind of abstract area in mathematics that arose kind of from the 1940s, 1950s. People looking at basically a way of systematizing different notions of structure preservation. We call them homomorphism in mathematics. It came out from sort of algebraic geometry and other areas. And these kind of principles started to come out, these kind of very abstract ideas, but looked like they could be a really useful organizing set of principles for mathematics. So you can think of category theory as about finding exposing mathematical structure and also the structure of mathematics. And it's now being used very, very widely across lots of different areas. In the Center of Mathematical Sciences, it's great to be doing this here because we have lots of actual real category theorists in the building, some in the sort of theoretical physics kind of zone, others in really pure maths, others who are applying this, others who are perhaps a bit like me who link this then with computer science. But it's a sort of way of thinking, a set of paradigms that has become quite influential in lots of different circles. So a bunch of recent books that I think are all quite relevant to what I'm going to talk about today. There's some really nice introductions about category theory kind of in the sciences. David Spivak has these two books. Applied Category Theory is also really nice, very nicely written book. This one's a bit better if you don't have a maths background. And this one, I like the ideas in here. It kind of puts together a lot of ideas, which I'm going to talk about today, using category theory as a way of organizing programming and thinking about the structure in programming, which is what we're going to do today in relation to kind of patterns that exist in lots of numerical codes, including in climate models. So what are we going to do today? I'm going to take some ideas which are hopefully quite familiar to you, kind of quite simple programming ideas, and view them through the lens of category theory. I'm going to teach you some elementary ideas in category theory, the notion of a category, a functor, and a natural transformation. These words probably don't mean very much to you right now, but don't worry, we'll get there. We're going to understand how they can be used to structure and understand patterns in programming. I'm going to show you a bit of Python code that relates to that. And then we're going to link those into ideas of testing and optimization in our code. So hopefully this kind of gives you just a bit of a launch pad. Category theory as a branch of mathematics is very, very broad and deep. It's about 70, 80 years old, so there's a lot of stuff in there. This is just going to be a little taste, something a little bit different at the summer school, give you a different way of thinking, some different kind of tools of thought, and then you can go and dig deeper on your own time. So what actually is a category? Category is a general mathematical structure which we're going to write down with a curly C. It has two collections of things in it. It has a collection of objects. We can think of these as kind of entities in some space, not objects in an object-oriented programming way, but we just sort of kind of entities that we want to represent. So we're going to use letters like A, B, and C as an abstract way of representing those. So we can think of a category as having a collection, which I'll write as obj-C, of these objects. And then we have a collection of morphisms, which are essentially some kind of relationships or connections between these objects. So I'm actually going to switch to writing things down. I really feel like I should be using the blackboard, but actually, for the recording, I thought this would actually probably work better using the iPad. So here we've got this cloud here. This is our category, and inside of it, we're going to have some objects. So this isn't anything sort of particularly concrete. I'm going to call the objects A, B, and C. Maybe we'll have another one over here as well, D. The relationship in the space is irrelevant. It's nothing kind of spatial going on here. So we have this collection of objects, A, B, C, and D. And then morphisms are linked between these objects, and they're directional. So they have a source and a target. So I'm going to draw those as arrows here. And we're going to use lowercase letters to name those morphisms. So I'm going to have F. I'm just kind of coming up with names here. Like this. And then down here, I'm going to list those morphisms, and we're going to use the single colon as a signature, and this little arrow notation to remind us what is the source and the target of the morphism F. And what is the source and the target of the morphism G? Goes B to C, and H goes C to D, like this. So we have a collection of objects and a collection of morphisms. We haven't really said what those are. It just depends on our particular example. This is kind of abstract at the moment. Now, that's not all we have. We have a bunch of other things in our category as well. We also need a notion of composition for morphisms. So composition is an operation that says, given some morphism F, let's say it goes from objects A to B, and given another morphism whose source matches the target of F, so we'll call it B, goes from B to C, we can compose these two things together, which I'm going to write with a semicolon, and then this goes from A to C like this. So you can think of it in the diagram as being able to follow these arrows. I can take a path from A to B, and I can go from B to C. Therefore, I have the composite path, F compose G, which is going to go between them. And this is the same as me following this path FG. The composite is the same thing. It's just now turned into a morphism itself. So for every pair of morphisms which can compose, then they have their composition. So for example, I can't compose F and H because B and C are different objects. They don't fit together. You can think of it a bit like types in a programming language. And in fact, that's going to be one of our major examples going forwards. So our category has a notion of composition. It also has a notion of identity morphism. So for every single object in the category, it also has a morphism called the identity morphism for that object that goes from the object to itself. I'm not going to draw maybe every single one on here. Maybe I can fit them in. So we've got one here. And we call it the identity morphism because it doesn't do anything when we have a composition. So if I go from if I go from A to B using F, and then I go on this little loop with the identity morphism back to B, that hasn't changed anything in the composition. It's the same as me just doing the F morphism. So actually, that's one of the properties, one of the axioms or laws of a category. It's called unitality. It says that for all morphisms F going from A to B, then if we compose F with the identity on B at the end, that's equal to just F, and that's the same as us doing identity on A and composing that with F. So this is a property that has to hold of categories. It's essentially saying that these identity morphisms are trivial. They don't give us any extra information. So this kind of concept of identity occurs all over mathematics. If you think of like plus with 0, times with 1, this is the same kind of idea, but at the morphism level. And I've got a little placeholder here for another law of the category, that's associativity. So if we have a bunch of morphisms, F, G, and H, that all compose, then it doesn't matter how we group those compositions. So we can do G compose H first, and then compose F on the front, and that's the same as us doing F compose G, and then compose H like this. So again, associativity is probably familiar to you from other bits of mathematics, like plus is an associative operation, multiply is an associative operation. So we're saying here the composition is associative. And that's all we need. That is what a category is. Objects, morphisms, composition of the morphisms, identity morphisms, and this associativity and unitality identity property. Now, that's very abstract. We're going to see some examples. Here on the slide, we have that definition serialized for us. I won't go through it again, but that just says what I wrote down. Let's go to an example, which is based on ordered sets. So any set of anything which has some kind of ordering can also be thought of as a category. So let's take the natural numbers, 0, 1, so on and so forth. It has an ordering less than or equal to, which we're going to use here. So 0 is less than or equal to 1, 1 is less than or equal to, and so on. So how is this a category? So we can take the natural numbers and have those be the objects of a category. So we've got a 0 object, we've got a 1 object, we've got a 2 object, and so on. We can have an infinite number of objects, that's fine. And then the morphisms are going to represent the ordering relationship. So because we know that 0 is less than 1, we're going to have a morphism between 0 and 1 is less than 2, so we've got a morphism there as well, and so on. So I'm actually in blue going to write down that relationship on the arrow to remind us that that's what that morphism represents. It's witnessing the fact that 0 is less than 1 or 1 is less than 2. So let's look at the properties of a category. We said that we had to have identity morphisms. Well, that's great. We do, because 0 is less than 0, less than or equal to, 1 is less than or equal to 1, 2 is less than or equal to 2, and so on. So the fact that we have this reflexive relation, reflexivity, is very close to the idea of having identities in the category. Now, this relation, less than or equals, is also transitive, right? So if I have 0 less than or equal to 1 and 1 less than or equal to 2, then I know that 0 is less than or equal to 2. And that's the associativity, that's the composition property that we want for our category. So we get all of these morphisms in between. And of course, there's an infinite number of those. We get all of these other ones going like this. So the transitivity gives us the composition. Reflexivity gives us the identities. So this works for any ordered set where the ordering is reflexive and transitive. Okay, yeah.
I guess initially the math will think of a morphism as like a function from the first object and the second object, but I guess here is a more general thing where it's like a statement that evaluates the true or false.
Yeah, really, yeah, good question. So we'll go to the intuition of functions in a minute, but you can definitely, one kind of intuition or one example of a category is to think of sets and functions. And these morphisms are really functions between sets. Here, it doesn't have to be like that though, so it's just a relationship. It's saying, okay, 0 is related to 1 by this relationship, and we can represent relationships in that way. It's called the classification function, representation of relationships. We say, if it's in the relation, then evaluate to true. But this is kind of a bit more abstract than that. Yeah, any kind of relations we could turn into this kind of category view. Yes? Yep. Yeah, this is a great question. So the question is, what about the greater than or equal to? Is it the same category or a different one? So that would be a different category. It would have the same objects but different morphisms, and they would be going the other way. It's not something I'm going to talk about today, but that would be known as the opposite category. If we called this category here n, math BB n, then the opposite category we would write as n op, and that would be the category that represents the greater than or equal to relationship. So this is a notion, it's called duality in category theory. If we take a dual, then we flip the direction of all the arrows. Great question. Okay, so let's go to the example that we're going to lean on today, which is the idea of categories in programming, where we're going to imagine that our programming language, and in this case it's going to be Python, is representing a category. And the objects of that category are the types, and the morphisms are the functions. So for example, I have a float type, that's one object, and I've got an int type, that's another object, and I have morphisms like the round function that goes from float to int. I've got the void type object down here, the print function goes from float to void, and I've got something that I've called pin code that goes from void to int, and I can have lots of morphisms between these things. I don't just have to have one morphism between things. Between any pair of objects, I can have 0 or many morphisms. So this is what we're going to use as our kind of analogy here for structuring our programs. We're going to think of this kind of ambient category of Python as our category here. So let's see then how the composition and the identities work. Yes, Robert.
Is a morphism from one object to another unique, or can you have multiple morphisms?
No, absolutely, you can have multiple morphisms. Doesn't have to be unique. In the ordered set example, that happens to be an example where the morphisms were unique, because there's only sort of one proof that 0 is less than or equal to 1. And that's called a discrete category or a thin category, where you have exactly one morphism between every object. But that doesn't have to be the case. And in our functions and types world, that's certainly not the case. There's lots of functions that go from float to int, for example. There's the ceiling, there's the floor, and so on. Thank you. Yes?
Can morphisms be multi-directional?
Can morphisms be multi-directional? No, so a morphism has a direction, it has a defined source and a defined target, but you could have a morphism going in the opposite way as well, going from one back to the other, and they could have some additional properties. So there are lots of examples of categories which have a whole bunch of other properties as well. The properties I've explained are sort of the essential core of what it means to be a category. But lots of categories have other properties, like they might have pairs of morphisms, which are isomorphisms, or retractions and embeddings and things like that. Great. So there's lots of things. You can describe a lot of stuff as categories, basically, I think is what we're seeing. So I'm going to write Python code that captures the rest of the stuff here. So we thought about this idea that, okay, objects are our types, morphisms are functions. So what's the composition? Well, that's just function composition. And I've written this down. Some of you perhaps were in my MyPy session, so I'm using the MyPy typing here to explain this compose function. We can read this as take a function f from object A to object B. Here's a function, a morphism from B to C, and we're going to compose them together to get something that goes from A to C. This is just the sort of MyPy Python way of explaining those function types. And so what do? I'm taking in an f, I'm taking in a g, and what I produce is another function, using the lambda here, lambda x, which first does f, passes it the input x, and then we pass that output to g. So it's just standard function composition. That's the composition of the category, and we can check it's associative. And then the identities, that's straightforward. That's just the boring old identity function. For every object A, for every type, we have this identity function that takes in an input and just returns it straight away. And that is the unit, the unit of the composition that has the identity property. Now, I will say that this is kind of an analogy in Python because it's sort of not exactly the case that the properties always hold, because functions in Python can do all sorts of kind of crazy stuff. They're not really pure mathematical functions. Functions in Python can go and mutate a global store, they can reflect on their implementation, they can go and print stuff out, and that can thwart properties like associativity and identities. We can actually kind of expose things that aren't that wouldn't be true in a sort of pure mathematical setting. So this is why I'm careful to say this is sort of somewhat of an analogy. Or if we restricted ourselves down to Python functions that were well behaved, that behaved like pure mathematical functions, say from set theory, then these axioms would hold. And there are other programming languages that constrain us down into this space. Languages like Haskell and Agda put us more into the sort of mathematical set theory, category theory world. Python, it's going to be a bit of an analogy, or we kind of think of a pure subset of Python that actually does have these properties. Okay? All right, so far so good. So, functors. Really, category theory is all about looking at relationships between things. The most important thing tends to be not the objects, but the morphisms, and about structures around those morphisms and how morphisms preserve structure. So functors are going to be morphisms between categories. They're going to be a way of mapping between categories, connecting two categories, in a way that's structure preserving. So let's jump back over to here. So to have a morphism between two categories, we have to have two categories. I'm going to call these categories C and D, and I'm going to use big F for functor. So that's going to be some map between these two things. And in C, we've got a bunch of objects already. We've got A, B, and C, and we've got our morphisms, F and G, and we've got the composite here. So what F is going to do is it needs to transform the objects in C into the objects in D, and it needs to transform the morphisms in C into the morphisms in D. It has to transform these two bits of information. So F is going to give us, on every object in here, it's going to give us an object over here. And I'm going to call these FA, FB, and FC. So there are kind of two parts to a functor, one that we call the object mapping part, that gives us FA, FB, and FC, and another which is the morphism mapping part. The morphism mapping part has to be coherent with the object mapping. So I'm going to use the same capital letter F. It's sort of like an overloading, but now it's working on morphisms. See that little f there. And now when we transform that morphism, it has to go from FA to FB. Not to some kind of other objects in the space, but there has to be a kind of connection between the object mapping part of the functor and the morphism mapping part. So we've got FG that goes here. And now we have to think about these composites. We should also have over here, because we had this composite morphism F composed G, then mapping that across also has to go from FA to FC. But notice that there's another path that we could take. We could go this way and this way. And in fact, that is one of the properties of a functor. We should have that the functor mapping preserves composition. So what that looks like is this. It says that doing the composition in C first, so this is the composition of the C category, and then mapping it across with F should be the same as mapping each part across separately and then composing them in D. Let's move that out of the way. So if we take each one of these morphisms, we translate it over here, and then we compose them. That's the same as us composing them first and then moving it over. So in a sense, this capital F, this functor, it doesn't mess with the structure of composition. It preserves it from one place to another. Yes?
Does it need to be the case that functor is a bijection on objects because the morphisms, the mapping for morphisms is determined by the object. So like doesn't matter, but could I send A to FA and also B to FA?
Yeah, this is a really good question. So the question is, does F have to be a bijection on the objects? Then the answer is no. We could actually collapse things down. So we could map A and B to the same object in D, and that's fine. There are properties of functors which are kind of generalizations to the normal set theory ideas we might think about. So injectivity is called faithfulness, and surjectivity is called fullness. So if a functor is full and faithful, it's like it's a bijection then on those things. So
Just for extra confusion.
yeah, well, there's some technicality there. There's some technicality to then what that means with the morphisms. But if you're talking about the category of sets, then those collapse into the same idea. But yeah, thinking of all these things, and people have thought about all of this. The functors, they don't automatically have to be bijective, though.
Can you explain what bijective means?
Yeah, absolutely. So a bijection is when we have a one-to-one mapping between sets. So I can just put this over in the side here. So a function is bijective if it maps from every object in one set has exactly one over here that it maps to, and everything in Y is mapped to as well. So it means there's a sort of one-to-one correspondence between the two sets according to this function. So it looks like a bit like this. Yeah. So that's just an aside. That comes from set theory and the work of Nicholas Bourbaki, which is a French collective of mathematicians who invented all these terms like bijections and surjections and so on. Right, so there's one more property of functors that we have to do, and that's the old identity morphisms, which I didn't stick in here, but we have to think about those as well. Those also have to get translated. Everything has to get translated. So we can have f of IDA over here, and this additional axiom says that when we move identity axioms across with the functor, they themselves are identity morphisms. So when I move identity morphisms, what you get is an identity morphism. So if I do f on IDA, then this is the same as ID on FA. So I'm using these subscripts to tell us what object the identity is working on. So notice we've gone from a subscript on A. This was an identity morphism that lived in C. And now this is an identity morphism that lives in D. So we're not changing the structure of the identities. It's all about this structure preservation. Yes?
So going back to this relation between functions and morphisms, you said the functor is a morphism between categories. I guess this whole time you've been speaking as if it's specifically a map, like a function that takes the first thing and maps to the second. So is a functor like more special, like more specific than a general like morphism that you have inside each of the 2000?
Yeah, good question. I've been using kind of terminology like mapping, like the functor's a function. Actually might not be a function. I'm just using that as a kind of an analogy. So there's something called cat, the category of categories. And in that category, the objects are categories and the morphisms are functors. But just like the ordering example, they might not be functions. They could be relations. They could be something else.
Okay, so these two categories themselves are part of a bigger cloud in which big F is the morphism.
Yes. Yeah, absolutely. Yeah, you know, mathematicians, once you give them one tool, they just start, you know, generalizing. So there's something called omega categories, which are like these infinite hierarchies of things. Okay, so how does this relate to programming? So these are just slides that say what I've said there on the things. We've got these two components that we have to remember, the mapping on objects and the mapping on morphisms. So this is just written in a more formal way. For every morphism A to B in C, we get a morphism that goes FA to FB in D. So functors in programming. So if our objects are types, the functor, what we're going to do is functors that go from our sort of Python category back onto itself. So the source and the target categories are going to be the same. This is technically known as an endo functor, endo sort of being onto yourself. So the object mappings are going to be type constructors because they map from types, the objects, back to types, objects. So the example we're going to use is lists. Lists are functors. From this day forwards, when you think of lists, you'll think, oh yeah, list is a functor. And you'll be able to understand what that means. So if list is a functor, it's got to have two parts, right? It's got to have the object mapping, maps from types to types, because we have to think, it's a list of what? We have to have types for the elements. So the source object is going to be the type of the elements, and our target object is then the type of lists of that element. So for example, if we take floats, then we can list as a functor, the object mapping takes us from float to list float, lists of float elements, or from strings to list of strings. What about the morphism mapping part? They provide a way to lift a function to work over then items that belong to that type constructor. So if I have a function now, A to B, the morphism mapping is going to give us a list A to a list B function. Does anyone here know of a function in Python that's like that? Map, yes, very good. That is the map function. So let's write this all out into code. And here I've got to do some typing. So lists are functors. So we have this object mapping, and that's already provided for us by the fact that list has been defined as a data structure, a parametric data structure in Python. So now we want this morphism mapping that lifts an A to B function into a list A to list B function. I'm going to write it like this. I'm going to call it fmap, like functor map. We want to take an A to B function, that's this thing, and get a list A to list B function back. And indeed, it is not implemented yet. I'm going to just not implement it for the moment. And I'm actually just going to start thinking about how I can use the category theory knowledge that I have to help me here. So I'm starting to think about this function. I'm thinking, yeah, this is like a really common operation, right? I want to sort of point-wise transform everything in a list. And we do this kind of thing all the time in modeling code, right? We have some sort of data structure like an array, and we want to apply an operation to every element in it. And then I think, it's a functor. So I'm going to write this implementation, but the functor tells me I have to have some properties. I have to have that. I have to have these two properties that tell me that it preserves composition and it preserves identities. These ones down here. So I can transfer those over into my programming domain and turn those into properties that have to be true of my implementation. And hey, I'm going to marry mathematics and software engineering today, and I'm going to do test-driven development with these mathematical properties. That's what we like to do in ICCS, mix disciplines. So I've got test functors here, where I've imported my functor and my category, and I've got tests based on these properties. So I've got a thing here that says, okay, if I apply on line 7, if I apply the identity function with fmap to some input data, then what I should get back is the identity function applied to that data, right? So doing the map function with the identity should not do anything. It should just give me back that bit of data, right? And so I've done it with 2 examples. I've got it with a little short list here, and I've got another one with the empty list. So these are values that belong to those objects. So it's like another layer below. Those are things that live inside the object. And I'm applying this functor property that the morphism mapping on ID should be the same as ID applied to that same input. And then I've got a test of that the functor preserves composition. So I've got 2 morphisms here, F and G. And then here I'm doing the composition. I could have just written those in a simpler way, but I've used my category.compose that's composing F and G, and then applying fmap. And I'm giving it a piece of test data here. And that should be the same as me first doing fmap with F, and then doing G with fmap as well. So I can use PyTest, run my things. Okay, it failed. All my tests failed because I didn't implement it yet. Fine. Let's go and write some code. So I need to return. I need to make a lambda because this is going to be a function that takes in the list input. And then I'm going to do map. I'm going to use the built-in map. Hopefully that works. Great, it works. So I have used the axioms from category theory to tell me about how this thing should behave. Now, does anyone know another name for this kind of property that we've done here? If we think of it as almost like an optimization. Has anyone seen this kind of thing before? Commutativity. It's not commutativity, although we could talk about that as an optimization as well. But we're not quite at convolutions yet, but we will end up in convolutions. So I'm glad you've mentioned it. This is perhaps more complex than I'm thinking. I'm thinking about loop fusion here. So if we think about this operation here, what we're saying is that we're going to do the map function, and we're going to do F and G together. So on every element in this list, we're going to do +1 and ×2 together. And we're going to go down the list and do both those operations together. So we only need to traverse the list once. We only need to do one map function. But down here, we have to do 2 traversals of the list. We have to loop through and apply +1 to everything first, get an intermediate list. Then we have to loop through that and do multiply by 2 on everything and get another list, which means I have to do 2 loops. So I've had to do double the amount of work, right? Because I've had to build an intermediate data structure. So a common optimization called loop fusion would see those 2 loops and say, oh, well, you can just combine them together and do those 2 bits of work in just one loop. I could have written this in a different way. It's the same. I could have done, excuse me. I could have written it like this. Does the same thing. Perhaps that reminds us there's a loop going on in here. And I've changed the implementation, so let's run my tests. Great, they're the same. So the category theory helped me write my tests there and have that nice behavior. And here's a definition where I've just put the input as I put the two arguments together. So I've got the function a to b, and I've got the input list as just another argument rather than having to build a function as the output. Those two things are equivalent. There's another bit of category theory that explains why those are equivalent. But I also might not be working with lists. I might be working with NumPy arrays. And don't worry, NumPy arrays are also functors. In fact, all collection data types, trees, lists of trees, NumPy arrays with other complex things inside of them, they're all functorial. So if it's a functor, I should be able to write this function. I should be able to take an a to b function and turn it into a function that maps from an nd array of a's to an nd array of b's. And yeah, I just did it with a loopy thing here in NumPy. And then I can check the functor properties again and make sure that it behaves in the right way. And that's what the rest of these tests do. They're basically the same kind of tests. It's those functor laws again. So perhaps I could make a version which doesn't satisfy these properties. Let's do something really silly that has like a global variable g, and then says g plus equals 1, and I'm going to do something really silly. For I in range 1 to g, now I'm going to do this first, and then I'm going to reverse. Oh, I don't remember enough Python. Okay, perhaps I should, ND array doesn't have this, so I'm going to do this on my lists instead, sorry. So bear with me, let's go back.
You can do it with the -1.
On MP arrays? Sweet, we're back in business. Is it a mutation, or is it?
Just put like out equals out, brackets colon -1.
Like that?
This might work if it's money out.
Wow, you get, let's see what happens. It test passed because of some other reason, I think. Oh, no, that's good. Assertion false. So here I've written something which is not a functor, because it goes and does some mutation. It kind of remembers how many times it's run itself, and it does something different based on those things. So that will completely break our tests, because in this case, we're doing one fmap. And so the first time we run that, we won't get any reversing. But then here we've got two fmaps, and it will do a reverse on one of them and maybe not the other. And so the multiplicity of the fmap is changing the behavior. So we've written something that's not a functor. And we're not going to be able to do loop fusion on that thing. And loop fusion is good because it's an optimization. This thing on the left-hand side is faster than the thing on the right-hand side. The one on the right-hand side has to traverse a structure twice, has to do twice as much work, has to also allocate an intermediate data structure. So not only are we getting principles about testing, we're getting principles about optimization as well that come from these rules. Some of these rules, we can orient them and see that they provide an optimization, and the rules tell us that it's the same thing. So we want our optimizations almost always to be semantics preserving. We want them to have the same behavior before and after, and that's what the category theory is telling us. And this was our non-example of something bad that we don't want to do. Okay, any more questions? Yes?
Well, going through the loop twice, I mean, is it really twice as much work other than the overhead of iterating through the list? I mean, what if the two operations are very expensive compared to the walking through the list?
Yeah, so if you have very, very expensive operations, then they would dominate the time taken, but you'd still have the time taken to walk the list. That might become a very small percentage, but it would still be there. I guess it's a question of how important is that to you. But it really is more expensive to do 2 loops than it is to do 1 loop.
And then maybe just quickly,
you got branching and, you know.
A less trivial example of a non, if you can't do loop fusion, I guess, would be like if you're looping through images and plotting them, but you want to have them all on the same color scale, and so you have to sort of run through the list once to check the global min and max. I guess you can't fuse those two loops. Right?
No, you can't fuse those two loops because there's another thing that has to go on in the middle there. So this is a really good question. Like, what about, essentially you're thinking like, I want to do one functor mapping, then I want to do something else, which is going to collect some summary statistics or something, and then I'm going to do another functor mapping. So a question you're asking there is, could I somehow commute these things so I can stick the two functor mappings together and then fuse them into one using my law? But that reduction summary thing will not be commutative with the functor mapping because it's going to do something to the data on the inside. So there are other bits of category theory that we can use to explain those things and look at when we're allowed to move things together. There's something called a catamorphism, which is a generalization to a reduction operation. And you can see how there's certain amounts of commutativity you get, but there will be an inherent barrier in what you're describing. So you might be able to group some things together, but then there will be a bit that you can't commute them over. It's a great question. Okay, so lists of functors. Natural transformations are morphisms between functors. Of course, we have to think about how to do morphisms between the things which were morphisms between things and so on. But this is a very important concept that we use all the time in programming as well. So let's say we've got two functors, f and g. They have the same source and target categories, so curly c and curly d. And natural transformation is a way of connecting those two together. And it does it by having a family of morphisms that live in D. So we're going to call it alpha. Alpha maps between f and g. So I'm using that arrow again because it is a morphism. It's a morphism in the category of functors. And it maps from f to g. And it does that by being a family of morphisms that says for every object A that's in C, I want to have a morphism in D that goes from FA to GA. So you can think of it as taking something that's in the image of that functor in D, the first one F, and going to the image of that functor G in D as well. So sort of mapping between the objects. But you think, oh, what about the morphisms? Well, that's already provided for us by the functor mappings, but we have to have a property to make this thing a natural transformation, which is called naturality, which says that alpha doesn't destroy the morphisms in the process. So let's see what it looks like. It's going to be some kind of way of saying that alpha lets us take one morphism in one place under the functor f and sort of preserves it over to the functor g. So I'm going to write this in a little diagram like this. This is called a commuting diagram. It's a very kind of common way of representing things in category theory, which is just, I was doing it all along when I was writing these little clouds with the arrows. These are just morphisms. The edges are morphisms, and the vertices are objects. So the naturality property says that if I have this object here, FA, and then I use my natural transformation, alpha A, to get GA, then I can lift this little f into the category, into D, using G, so I can go from GA to GB like this. So that's going from one way round. And the other way round is going to be equal to that. So if we follow two different paths in the diagram, if they end up at the same place, we say they're equal. So it's like a kind of, imagine an equal symbol here. So on this side, first we use the functor f to lift our little f from FA to FB, and then we use alpha, but now the B version of it to map FB to GB. So remember I said alpha is it's a family of morphisms. It's like you can think of it as a whole bag, a whole collection of morphisms, one for every object A in C. So that's why I use the little subscript there. So this time we were using the A version, and here we're using the B version. But this naturality property kind of relates all of these things together by this property. That it's not just sort of an arbitrary bag of stuff. They have to behave in this way. And this naturality property really tells us something very deep about how they are connected. We're going to see an example back in our programming land. In fact, I'm going to do it on the old iPad first. Natural transformations. So I'm going to introduce to you another functor. We had the old list functor, which we know and love. I'm going to make a very, very basic functor, which is called ID. It's the identity functor. It goes from some category back to itself. And on objects, it's the identity. You give it an object A, it gives you A back. And on morphisms, it's the identity. You give it a morphism, it gives you that morphism back. So it's sort of like very boring. But it's kind of a useful technical device here, because I'm going to describe to you a natural transformation called, I'm going to call it generate. Sorry, changed my mind. Generate. Generate on A takes something from the functor ID A to list A. So it's a natural transformation between the identity functor and the list functor. I'm going to give its definition. I'm going to write some like Python code or imagined Python code. It's a lambda x, and it returns a singleton list with x in. So, you know, IDA is really just equal to A, right? So this is a function that goes from A to list of A. Takes a value of type A, and it turns it into a singleton list of elements of type A. Really simple function in Python. This is a natural transformation. Why? Because it has the naturality property. It says that if I start off with IDA and I do generate, so I'm just going to call it gen, and I get list of A, then I can use my list map, so list of F, or in the Python code we called it fmap. And that gives me a list of Bs. That's the same as me first doing the ID of F, which is really just the function F, to get IDB, and then doing the gen over here. So let's do this with a concrete bit of data, which I'm going to do in red here. So imagine coming into here, I have the number 42. If I follow this way around the square, I get a singleton list of 42. And let's say our function f is equal to doing +1. So when I go down this way, what I get is the list with 43. Okay, so I'm like evaluating this now, going around the square. Now if I do f first, I get 43. And then gen just puts it into a singleton list, so I get the singleton list of 43. So you can see it's about this kind of commutativity between the gen operation and the two functor mappings on either side. And maybe we could have gen be something more fancy. Maybe this was actually making a really big array of stuff, a whole big thing that was quite large. And so, you know, we'd be doing this. I'm going to kind of write ... to imagine it's just really big. So say it was a bit like the, I don't know, the zeros operation in NumPy or something, or some other kind of generalization where you want to take some particular value and make a big array of that value. Now, again, we're getting both a property that we want to check, and we're getting an optimization, because notice that this way round the square, going on this side, we only have to apply f once, and then we copy the value to make an array. But this way round, we have to copy a value to make an array, and then traverse through the array doing a loop and going and transforming all of those elements. So this way round is going to be slower, whereas this way round is going to be faster. We only have to apply f once, whereas on the other side, we have to apply f however many number of times that thing is in the array. So in the code, which I won't go through at length, but you can check it out later. I've called it promote here, sorry. Promote, that's a natural transformation, and then our tests check that it has these properties. It checks the naturality property here. I've got another operation, which is a natural transformation. Doing reverse on a list, that's a natural transformation. It has these properties as well, which are tested. And then I've got this reverse bad, which was like the thing I did before, which was showing a version which is not natural. So you can go and you can run those tests. I think I didn't put tests in for the one that's bad. But yeah, you can see the naturality properties hold for reverse and promote. So something very deep about naturality it's telling us that these operations, they're going to change the structure of things. Functors are about structure. It's a mapping between structures, but it does it in a way that you can't change the stuff that's on the inside because it has to work for every object. I can't go and take something in this list and multiply it by 2 because this has to work for all types A. It has to work for every object A. We don't know that we can do multiply by 2 on those objects. Those things inside could be network sockets or Cartopy objects or something that we don't know how to do multiply on. So the naturality is really about, it relates very closely to polymorphism and the properties that polymorphism gives you. If you were in my MyPy session yesterday, I sneak previewed this naturality property and talked about how parametric polymorphism really constrains our set of possible operations that we can do. We have to do sort of just structural things to these bits of data. We can throw stuff away, we can reorder them, we can copy them, but what we can't do is actually change something about those elements, compute with those elements. We just have to preserve them. So lots of sort of structural transformations that you might want to do with your data, like reshaping, those are natural transformations. If you're writing a function, you want to reshape this grid into this thing, you should think, I'm not changing the elements. Maybe it's a natural transformation. Maybe I could write a test then that tests the naturality property, that doing the functor mapping first and then converting should be the same as converting and then doing the functor mapping on the other side. That might also be an optimization depending on your data structure, might not be. In this case, the promote naturality does give us an optimization. For reverse, not an optimization. Reversing, we still have the same number of elements. Reverse, whatever the length is here, it's the same as the length out. So the naturality is no optimization there, not particularly. It's unlikely to really be an optimization at all. But it's still a property that we would want to hold here and check, does this thing actually preserve those elements inside? Yes, Rob.
Say you have some sort of promote, like go from a list to a 2D array.
Yep.
So you have like the flatten operation.
Yep.
How does that fit into this?
Yeah, absolutely. Flatten should be a natural transformation because it doesn't change the stuff inside, it just reshapes it. So you're writing your flatten function, you think, I'm going to write a test for this. The test is the naturality property. This one. You just have to also have the mappings for your flattened representation and your non-flattened. Yeah, great. So we've done that one. Right, so I've been kind of alluding to the connections back to kind of basic ideas in numerical modeling. It's not super specific to climate modeling necessarily, but these nice examples of reshaping data. Functors are about doing these point-wise traversals, like maybe you're doing this kind of completely local model of something where you're transforming the data at each step. I'm sure you've all written these kind of point-wise loops over arrays and things before in Fortran or Python or whatever. That's a functor. Many of these structural transformations, as we said, like these reshapings, those are natural transformations. So hopefully I've given you these ideas about how we can take these properties, turn them into tests, and sometimes turn them into optimizations as well. Now, in the remaining few minutes, we've got 6 minutes left, that's perfect. Let's go a little bit beyond functors. Let's think about stencil computations. You're solving the Navier-Stokes equations because you're writing a dynamical core or geostrophic equations or something. These are actually very related to functors. They're a generalization of functors. So this is a structure called a comonad. Co in category theory means that something's been flipped. It's a dual. So there's also a thing called monads, which if you want to talk to me about monads, I can talk to you about that later. Monads are a way of describing, they're quite nice for actually explaining how programs transform state or transform the context they're in. But comonads are another kind of structure. They start with an endofunctor. So a comonad comprises an endofunctor. I'm going to call it D. It maps from C back to itself. And then a comonad has 2 operations along with it. It has a natural transformation, which is called epsilon typically, that goes from D to identity. It's like the opposite of that promote that I was just talking about. So we go from DA to A. So you can think of this, it might be like taking a list and taking the first element of the list would satisfy this signature. So this has this thing, it's called the extract or the co-unit. And then it has a morphism mapping. that takes a DA to B morphism and turns it into a DA to DB. Now, this is a little bit like our functorial mapping. Remember, our functorial mapping takes a morphism A to B and turns it into a DA to DB. And we said this was like, apply this in our array example or list example. It was apply that function to every element in the array. But if you're thinking about doing a convolution because you want to solve a PDE, you can't just look at every element. You have to look at a local neighborhood. Say you've got your numerical analysis textbook and you've done some Taylor approximation. You've got centered depth of 1 kernel to do a convolution. You need to pull in the local element and a small neighborhood, say the element to the left and to the right. That's what's captured by a comonad, because this isn't just taking in a single A, it's taking in DA. But it's not any DA. There's other axioms of the comonad. There's 3 axioms that I'm not going to show you, but they tell us about what this has to be. And what it has to be is a kind of way of taking a local function and lifting it to global. Let's see an example. So arrays are comonads as well. So I'm going to take this DA to be an array, but it's an array that's also paired with an index into the array. We call it a cursor. So this is, you can think of it as a pair. We've got some indexing set, could be like pairs of integers if it's a 2D array. We've got an array that maps from pairs of indices to A's, and we've paired it with a particular index. And I'm in this little pictorial representation, I've got my little grid as the array. The gray thing is like the place where the index is pointing. So our epsilon operation is going to return the value at that position. We don't need to worry too much about this operation. But what does this lifting thing do? So if we take a stencil computation, f, given an array with a location at the array that we can think of as like our current position. If you imagine a big for loop, it's like our indices where we are at the moment in that array. And what this function can do is compute a kernel, compute a convolution at that position, maybe look at some neighbors and compute a result B. So do that little convolve. And that B is going to be the sort of B that corresponds to this middle position here. What the lifting does is it takes that operation and it applies it at every point in the array. It takes a local computation and it applies it globally. So if this is you're solving the fluid equations, it's going to go over every position and going to localize the input at F to that particular position, and it's going to do it there, all the way so that we can build an array at the end. Because look at the types. Oh, sorry, the type's not on here. This is DA to B, and now this is DA to DB. So we're generating that structure out at the end, and we're doing that by traversing every point of the space. Now, it's the actual axioms of the comonad that force that to be the case, and I won't get into that, but the array comonad has to do this. It has to visit every point, a bit like how the functor has to visit every point, but it has to do it in a way that's taking a local to a global. So the dynamical core of your atmospheric model or your ocean model is built on comonads underneath, these kind of traversals. And you could restructure your code in this way, or you could be thinking, I need to implement this dynamical core, and I want to do it on this kind of grid data structure, and I need this little core, which is applying a stencil to every position in this data structure. Well, here is your nice recipe book of properties it has to have, how it has to behave, some optimizations as well. You go and look at the comonad definition and its properties. But unfortunately, that's like another half an hour's worth of work to go through all those properties. So I will leave it there, and I can put more notes on that later. I do have the code for this example online as well. So we looked at these kind of common ideas in numerical programming through our category theory lens. You're super focused, which is great. We learn about categories, objects and morphisms, composition and identities, functors, which are really morphisms between categories. They have to preserve the composition structure, and then natural transformations, which were morphisms on top of that, which had to preserve the functorial behavior from one place to another. We saw how those related to things we already knew and loved and were actually really quite simple. Map on lists is something that you've probably seen lots of times, but we saw this categorical lens let us think about its properties. We can use those for testing. Testing is good. We should always be writing tests in our code. We can use that to guide our implementations. and sometimes get optimization strategies as well. So I'll leave it there. Some of these books are really nice if you want to kind of dig in a little bit more, and the code and the slides you can get online. I'll put the link into the Slack as well. And yeah, thanks very much.